Pluto is a distant and mysterious dwarf planet, once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen? And what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon? Or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets, which could be a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacy of space mechanics. The three-body problem in space is about figuring out how three things in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic. Minor deviations in initial conditions lead to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the big planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Jupiter's gravity alone is strong enough to keep Pluto on a stable path for a really long time, even billions of years. These phenomena are essential in the context of the universe for maintaining the order and predictability of space's movement. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Pluto's orbit is a remarkable example of celestial mechanics at play, demonstrating both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, showcase the intricate and dynamic nature of space. Predicting cosmic events, especially when it involves chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainty. While numerical simulations provide a powerful means to understand and anticipate the future paths of celestial bodies, they also highlight the limitations in our predictive capabilities. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, despite all these complex forces trying to keep such an event from happening? Neil deGrasse Tyson and Michio Kaku, both prominent figures in astrophysics, have expressed concerns about a potential collision between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a rare and catastrophic event in our solar system. The collision would release an immense amount of energy, likely shattering Pluto given its smaller size and icy composition. Debris from the collision could spread across the solar system, potentially creating hazards for other planets and their moons. For Neptune, such an impact could alter its atmosphere and potentially its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory, brings a unique perspective to the debate as well. His views on the future of space exploration and the interplay between celestial mechanics and theoretical physics offer deep insights into the mysteries of space phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto can provide crucial insights for future space missions. This knowledge can help in navigating the solar system more effectively, predicting potential hazards, and even in the planning of missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, offering a blueprint for how we might approach and understand distant worlds. When it comes to the physics of planets, celestial mechanics and theoretical physics are deeply related. The movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are connected to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astrophysics, offering a unique observational opportunity that could potentially relate to string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The collision could produce extreme conditions of energy and gravity, potentially creating scenarios where effects predicted by string theory might become observable. For example, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, a key interest area. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit is a remarkable example of celestial mechanics at play, demonstrating both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, showcase the intricate and dynamic nature of space. The three-body problem is not the only mystery of the universe that we have yet to find answers for. Many other potential catastrophes are predicted to occur, highlighting the ever-evolving and dynamic nature of space. Understanding these patterns helps us learn more about how planets move in space, especially when they are really close to each other. Rogue planets drifting through space without a star add another unpredictable element. These planets, once part of a star system, get ejected due to gravitational disturbances or other celestial events, such as the close passage of another star or the dynamic instability in multiple systems. Over time, these rogue planets drift in space, traveling vast distances and potentially entering regions far from their point of origin. During their lonely journey, they carry with them the potential to cross paths with other star systems. If one of these wandering planets crosses into another solar system, there's a small chance it could collide with a planet in that system. However, space is incredibly vast and mostly empty, making the odds of a rogue planet directly hitting another planet very slim. The sheer scale of interstellar distances and the relative rarity of planets in open space act as buffers against frequent collisions. Pluto's enigmatic dance around the Sun continues to captivate scientists and enthusiasts alike, offering a window into the complexities of celestial mechanics. While its classification as a dwarf planet sparked debate and redefined our understanding of planetary bodies, recent revelations about its orbit have reignited interest in its role within the solar system. Neil deGrasse Tyson and Michio Kaku, two prominent voices in astrophysics, have raised concerns about a potential collision between Pluto and Neptune, shedding light on the intricate dynamics at play in our cosmic neighborhood. Their warnings underscore the importance of understanding the gravitational interactions and orbital mechanics that govern celestial bodies' movements. Pluto's orbit, characterized by its eccentricity and steep inclination, defies conventional expectations and challenges our comprehension of planetary motion. Unlike the relatively circular orbits of its neighboring planets, Pluto's path traces a unique trajectory, intersecting with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, particularly Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over millennia despite the chaotic nature of its trajectory. Numerical simulations have revealed underlying patterns and mechanisms that help regulate its motion, preventing catastrophic collisions with neighboring celestial bodies. The three-body problem in space involving Pluto, Neptune, and the Sun epitomizes the intricate interplay of gravitational forces and orbital dynamics that govern the behavior of celestial objects. Understanding this complex system requires sophisticated mathematical models and computational simulations, which provide valuable insights into the long-term evolution of planetary orbits. Pluto's status as a dwarf planet has sparked debates about the criteria for planetary classification and the diversity of celestial bodies within the solar system. While its small size and distant orbit set it apart from the traditional definition of a planet, Pluto's significance as a celestial object continues to inspire scientific inquiry and public fascination. The study of Pluto's orbit extends beyond the confines of our solar system, offering insights into broader astrophysical phenomena and the fundamental principles of theoretical physics. Michio Kaku's expertise in string theory and theoretical physics brings a unique perspective to the discussion, highlighting the interconnectedness of celestial mechanics and the fundamental forces that shape the universe. The potential collision between Pluto and Neptune raises intriguing questions about the long-term stability of planetary systems and the factors that influence their dynamics. Exploring these questions deepens our understanding of the cosmos and provides valuable lessons for future space exploration and the study of other celestial bodies. The exploration of Pluto and its orbit exemplifies the boundless curiosity and ingenuity that drives scientific discovery. As we continue to unravel the mysteries of our solar system and beyond, the story of Pluto serves as a testament to the enduring quest for knowledge and the ever-expanding horizons of human understanding. If this was a news article about a possible collision between Pluto and Neptune, it would be a stunning revelation, highlighting the importance of monitoring and understanding the complex dynamics of our solar system. The story of Pluto's orbit and its potential collision with Neptune underscores the delicate balance of forces that govern celestial mechanics and the ever-evolving nature of space phenomena.